तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome everybody again to the lecture series on computer graphics. And in the last few lectures we have been discussing how to draw lines and circles on the screen using an integer based algorithm, how to draw it as efficiently, as fast, and as fast means quickly, and as how accurately also as possible. And the criteria for drawing points, pixels for a line or a circle has been the midpoint line criteria or Bessenham's algorithm for drawing lines and circles. And we had seen an example also in the case of a line as well as in the case of a circle, where we not only used first order differences, but also the second order differences to come up with an integer based algorithm, where within the loop you increment the first order differences by integers only, and to that is how you update the first order differences and get the next value at of the function at the next midpoint and so on. And basically at each iteration you have only two choices between the next two pixels to choose from, correct. So in the case of a line, if you remember, you had to choose from between east and northeast pixels because we were operating in the first quadrant. In the case of a circle, you are basically operating in the second octant to be precise, and once you are choosing points within the second octant, the choice was basically between the east and southeast pixels. So we know these two different criterias, in fact the same criteria but in two different methods for a linear case of a straight line and for a nonlinear case an equation for a circle, how to evaluate and draw points. The last of these functions which we will see today is how to draw an ellipse. Now we had discussed this earlier, that a circle is a special case of an ellipse. So if you actually have the equation and a method of ellipse, you can actually draw a circle, although as a special case we had seen equations of a circle separately and evaluated the midpoint criteria and also seen how to draw the algorithm, correct. So today we will start with ellipse, okay, ellipse drawing algorithm using midpoint criteria, Bessenham's drawing for method of drawing an ellipse. Let us look at the first slide. So the ellipse drawing method, scan conversion of an ellipse, is what we have to see, and this is the example of an ellipse in two-dimensional coordinate system x and y, where you see this equation, it's centered at the origin, that is what we assumed, and we don't bother in fact if it is not at the origin or if it is also not aligned with the x and y coordinates. We know how to do two-dimensional transformations and then put it at any point in 2D space. Okay, as you can see that the ellipse intersects the x-axis at 2 points in positive and negative direction, and also the y coordinate along in the positive and negative direction. The difference in the case of an ellipse with respect to a circle is this intercept value plus a and minus a along the x-axis, and the intercepts plus b and minus b along the y-axis would have been same. That is, the value a and b would have been same. In the case of a circle, in the ellipse, a is typically not equal to b. A special case of a is equal to b is the case of a circle. Okay. Let us look at the equation of the ellipse centered at the origin. where we will say the x axis is considered as the major axis of the ellipse, where the intercept is larger and the intercept along the y axis of distance 2b plus b to minus b is the minor axis. The equation of an ellipse is v square x square plus ay square. It is represented in the form of an implicit representation. Actually, it can be written as x square by a square plus y square by b square is equal to 1. That is the typical expression of an ellipse, but we know now that in the case of circle as well as for the case of a line, we have represented this functional form as fxy equal to 0. So, that is the equation of an ellipse in the form of fxy equal to 0, where the length of the major axis, that is the x axis, basically is 2a and the length of the minor axis is equal to 2b. Okay. So, 2a and 2b are the intercepts along the major axis and minor axis. I did say again that x axis is the major axis in this case, intercept running from plus a to minus a and plus b to minus b for the minor axis. If a is equal to b, then the special case of an ellipse becomes a circle. Good. Let us now look at the pixels which lie on the ellipse. If you look into the first quadrant of a part of the ellipse which has to be drawn from the figure before, slide before, if you look at the slide before, you can see that if you draw only the points on the first quadrant, then by symmetry you can obtain the points in the other 3 quadrants. This concept was also used in the case of an circle, where basically we had an 8-way symmetry, correct, where we found out the points lying on the second octant, you remember second octant, and all the other points were obtained by symmetry, 7 points, other 7 points in the 7 octants corresponding to a point in the second octant, which was evaluated by the algorithm. The other 7 points in the other 7 octants were automatically obtained by symmetry. Now, if you look into the circle and if we see the points on the first quadrant from the positive intercept plus b on y axis to the section of the curve up to plus a on the x axis, if we somehow get these points by the algorithm, the rest of the points can also be obtained easily by symmetry. So, applying the same logic, we can only have we have to basically find out 1/4 of the set of points of an ellipse, unlike the case of 1/8 in the case of a circle. So, we look at the first octant, the first quadrant, and this is the first quadrant which is shown again here. And as we see here that the reason why we can't talk of octants but quadrants only in the case of an ellipse is that the choice of the pixels vary from one region within a quadrant to a second region. If you look at region R1, if after any particular at any stage of iteration, if say this is the current point marked here by the cursor, then the next choice of the next pixel will be between east and southeast, because this is the slope of the curve is basically in magnitude less than 1. Okay, that is why the choice is between the east and the southeast pixel. In region R2, the choice is between the south and the southeast pixel. This is the case where the portion of the ellipse is nearing the x axis and the slope of the tangent to the curve in the region which we will say as R2. We split the first quadrant into 2 regions now, R1 and R2. Okay. In the region R1, the slope of the tangent to the curve at any given point is less than or equal to 1, and in R2 the slope is more than unity. So, hence this is the reason why in region R1 the choice is between east and southeast pixel as clearly marked by 2 other points in this square grid in region R1, and in region R2, if this is the point at any stage of iteration chosen, the choice in the next iteration will be between south and southeast pixels. That is because the slope actually is more here, it is more than 1, and hence the choice is between south and southeast pixel. So we have two regions R1 and R2, and we have to have two different conditions of the choice of the next pixel based on Bressenham's algorithm. The same concept as the case of a circle could be used here, but the choice is not like that we have done in the case of the second octant for a case of a circle. Whatever we did for the second octant is basically valid for region R1. In region R2, the choice has to be now between the south and the southeast. And there exists a point on the ellipse where the two regions meet, that is the place where the tangent to the curve has a slope is equal to -1. As you see here, the slope is equal to -1 at a point which is the demarcating point between region R1 and R2. The points from the y-axis, the points on the curve from the y-axis to this point lies in region R1, and from this point to the region to the x-axis lie in region R2. So this is the point where the tangent to the curve, I repeat, the tangent to the curve is equal to -1, and if you are in region R1, the slope is less than -1 in terms of magnitude. Okay, if you take the magnitude of the slope, and in here the magnitude is more than unity. That means in negative direction it is actually less than -1, but in magnitude it is more than 1. So these are the two regions which we have to see now and write two different conditions for the Bressenham's criteria for integer based algorithm, and look at the first order difference and see what we get. So the task is to draw pixel in both these regions R1 and R2, and that helps us to fill up the pixels in the first quadrant. The points in the other quadrants I just informed you earlier are obtained using symmetry. That means once you have obtained all the points in region R1 and then the and the remaining points in region R2, this helps you to obtain all the points in the first quadrant. If you find out points in region R1 and then points in region R2, together they form the points in the first quadrant, we know that. Then using symmetry you can obtain the rest of the 3 points in the other 3 quadrants. For any point you can obtain the 3 points in the other 3 quadrants, but if all the points in a particular octant, in this case the first any quadrant, that is the first quadrant is known to us, the respective points, all the other points in the curve in the other 3 quadrants can easily be obtained using symmetry, we know that. So that is the other point, points in other quadrants are obtained using symmetry. And we are also seen the necessity now to obtain the point on the contour or on the curve on the ellipse, the contour or the curve on the ellipse, where the slope of the curve, that is basically the slope of the tangent to the curve, is -1, because that is the point which will demarcate the region R1 and R2. Isolate the curve into 2 parts, one belonging to region R1, another belonging to region R2. We have seen that diagram as is given here. Part of the curve is in region R1 and the rest of the curve is in region R2, and we need to find out this point on the curve where the tangent to the curve has a slope equal to -1. So that's a task which we need to do first. Okay. So once we are able to get this point, this helps to demarcate regions R1 and R2, that also we know. Okay. And the choice of the pixels, as informed before and as given here in the figure at the bottom, that the choice of the pixels in region R1, choice of the pixels in region R1, that is from the y-axis to this point which splits the curve into 2 different regions. The choice of pixels is in R1 is between east and southeast pixels, whereas in region R2 it is between south and southeast pixels. Region R2 it is between south and east. So if you get this point, it's easy for us because you have to apply the choice between east and southeast for R1, south and southeast for R2. So how to get this point? The point can be obtained by trying to find out the slope to the curve. How do you get the slope for the curve in a functional form? Fxy is equal to 0. The fxy in the case of an ellipse is given here, okay, which is b square x square plus a square y square minus a square b square equal to 0. So that's the implicit form of the expression for an ellipse, and we need to get the tangent to the curve, which is given by the grad function. Differential, remember f is a function of x and y, although it is capital F and small f here, but don't worry, this is the same functional form f here, and grad of f x y is nothing but partial differential with respect to x I plus partial differential of f with respect to y. I and j are the unit vectors along x and y respectively. Assume, so this is a vector notation of grad. I is the unit vector along x direction, which is horizontal to the right, and j is the unit vector along y axis, which is a vertical vector pointing upwards. So these are two unit vectors, and the grad is the partial derivative of f, capital F again. You can use capital or small f interchangeably, but they are the same in this case, and so take the partial derivative with respect to x and y. What is f with respect to x? You see that there is only one term with respect to x, so that is what you have to differentiate. So you will get it as 2b square x. So it is given as 2b square x here. Partial differential with respect to y is only again one term with respect to y, so you will get as 2a square y. Okay, so 2a square y is your del f del y, and del f del x we have seen is 2b square x. So that is the grad function. The grad function is hence defined as del f del x with a unit vector along x direction, and del f del y, that is the partial derivative with respect to y direction with the j vector, which is unit vector along y direction. So it is 2b square x unit vector along x, 2a square y unit vector along j. Now if you look at the components of this grad function, which gives the slope of the tangent to the curve at any point on the ellipse, you will see now that in region R1 you have the partial derivative along x to be more than the partial derivative along y, and in region R2 the partial derivative along y will be more than partial derivative along x. If this happens, only then the slope of the curve actually is numerically less than 1 in magnitude on region R1, and then the slope is going to be more than 1 in region R2. We are not interested in the actual value of the slope at each point in region R1 and R2. We are going to use these equations of grad, the equation of the grad for the ellipse, to obtain the point on the ellipse where the slope is equal to 1. Is equal to minus 1 basically. So at that point what will happen is, at the region boundary, what is the region boundary? The point which is the meeting point of region R1 and R2 on the ellipse, the partial derivatives of along the x and y directions are both same. So this is the property of the grad function which we will use to obtain that point on the ellipse, which is as a demarcation point between region R1 and R2, because we will start at some point and we must know at any given point of time whether we are drawing pixels within region R1 or we have actually crossed over to region R2. So this is the condition which we will use, and if you have a look at this condition, based on this condition we obtain the criteria when the next midpoint moves from region R1 to R2, and that midpoint is if xp yp is the point or pixel chosen at any given stage of iteration, the next point will be xp plus 1, next midpoint will be xp plus 1 yp minus half, because we are basically going to the right along x direction 1 and minus half in the direction, because the choice has been between, remember, east and southeast in region 1. Okay, so that if that is the case, that is the next midpoint which you are already choosing, and we find out whether the next midpoint is already here, otherwise carry on in region R2. If not, if this condition is satisfied, then we have moved on to region R2. And remember, this is del f del y is equal to del f del x, so and del f del x is more than del f del y. So based on this, when the above condition occurs, we switch from region R1 and move on to region R2. Okay, so this is the condition which we will keep in mind, which will help us that to know that we are moved into region R2 from region R1. Okay. This is these points are obtained from the grad functional formulas which we have defined and derived in the previous slide. Okay. So analysis in region R1 can continue. Let the current pixel be xp comma yp, and I defined the old value of radiation variable d. We are known to these terms, we have used it in the case of line drawing, we have used this in the case of an ellipse drawing. So, we use the same terminology. I hope you remember all of them. We have worked it out and we use the same. I do not need to redefine this term of the decision variable. D start will have to be evaluated, D at the next point, whether it is east and southeast or south and southeast, we can all work out. So, let us look at this slide. Analysis in region R1 involves that let the current pixel be xp comma yp, and the d old is a function of f next midpoint. That one subscript indicates that we are analyzing in region R1. The subscript 1 indicates that we are in region R1. Okay. So, fm1 is the value of the function f at the next midpoint in region R1, which is a d old, which d old subscript old indicates the current value or the old value is xp plus 1 yp minus half. This is because the choice is between east and southeast pixel. Since the choice is between east and southeast pixel, the next midpoint will have will be shifted by 1 pixel along x direction and minus half along y direction. And if you substitute in the value of f, which we all know, you will get this expression for fm1 or d old. So, just keep this in mind. This is the d old formula, the old or the current value, as you can say, for the decision variable d. We are working in region R1 and we have two choices. If we have a choice east, that is because that the d is less than 0, that is the midpoint is basically within, the midpoint is within this circle. You have to remember that the choice is between east and southeast pixel, and if the curve is passing over the midpoint, the curve is closer to the east pixel, so we choose, and when the curve is closer to east pixel, the midpoint is below the curve, the decision variable will have a negative value. You can easily visualize that because we have done it for a circle, we have done it for the case of a line in the previous case also, and for the ellipse the same criteria for D, positive or negative, a Boolean decision to be taken whether you need to choose east and southeast. So, we know that when D is negative or less than 0, you have to choose east. So, for choice east, the new value for the decision variable D is given as this. Look at it. It is xp plus 2 yp minus half, because you have chosen east. So, the next decision variable will be xp plus 1, which is already there for the next midpoint, plus 1. So, xp plus 2. Okay, and we substitute this xp plus 2 and yp minus half respective coordinate values into the expression of f. This is the value of d nu which you get, correct? You can work it out yourself. Please do not simply copy from the screen which you are seeing, try to work it out yourself, and then I will halt and tell you to find out, if I try to express d nu, which is given as this expression, in terms of d old, which is given on the top, as you see the expressions are almost similar. Lot of terms are matching, especially the last two terms are exactly same. The difference between these two terms basically comes with the xp variable. What will be the difference? I can look at d nu minus d old. What will be d nu minus d old? If we can evaluate that, then I can write d nu as d old plus something else. What will be that something else? If you evaluate, you will find out that it will be b square multiplied by a 3xp plus 3. Okay, just find out, because you will have 4xp minus 2. So, you will basically have 2xp, b square multiplied by 2xp plus 3. Let us check it out if it is correct or not, that is it. So, you have d nu as d old, which is this expression on the top, plus this term. This is the additional term which is coming due to xp plus 2 whole square, correct. So, this is the term which will come. So, if this is the case, I can define my first order difference. If east is the choice in region R1, E and 1 subscript for the delta D indicates that I am looking at first order difference under the condition that I have chosen east in the first region as b square multiplied by 2x plus 3. Please note down and mark this in rectangular box. This is one important formula which is going to be used in the drawing, in the case of drawing an ellipse. Let us look at the choice. If the choice is southeast, if choice is southeast, the decision variable is positive or equal to 0. Why? What does this mean? That means between east and southeast, the midpoint is above the curve. Okay, the ellipse is passing in region R1 and the midpoint is above, the curve, and the choice is between east and southeast pixel. So, the midpoint is above the curve curve is closer to the southeast pixel, and hence the southeast pixel should be the obvious choice. And since the point is above the curve, you have the decision variable d at the midpoint to be positive, greater than or equal to 0. Equal to 0, you can choose east or southeast. In this case, we have chosen it to be southeast. And in the case of southeast, the d nu, as in the case of east, will now be xp plus 2, that is fine. But since it is southeast, you have yp minus half minus 1. So, you have yp minus 3 by 2, that is the expression. Substitute these values into the expression of f, you have this expression, b square multiplied by this term, a square multiplied by the y part, and of course minus a square b square, which is obviously cancelling out. Now, I have to again do the same as I have done for east. That means I must try to write d nu as d old plus some factor. So, to do that, subtract from d nu the d old. As you can see now, that only one of the term, that is a square b square part, is the one which will be cancel out. That term will be having b square multiplied by an x factor and a square also minus y factor. Okay. Okay. And what do you get? You get b square multiplied by the same 2xp plus 3, all right, but a square term will contain minus 2yp plus 2. Please check it out. Please check it out. When you subtract y square minus half whole square from yp minus 3 by 2 whole square, these two terms are important. When you subtract one from the other, the term here is to be subtracted from this term, is where you get the coefficient of a square. So, I hope these equations you can work it out yourself. Please do it right now and verify and see that the first order difference, if southeast has been the choice and you are in region R1, is given as b square multiplied by 2xp plus 3 and a square 2. So, these two formulas are very important. First order difference under the condition of east pixel in region R1 and first order difference in the case of southeast pixel in region R1. Okay. If you remember these two expressions, we can move on to the next slide. I think you do not have any objections. So, we move on to the next slide, remembering just this first order differences in region R1. We need to find an initial condition now, correct. So, in the region R1, the first point is 0 comma b. So, what is d start, or in this case we will say is d init, is after the first point 0 comma b, the next midpoint will be 1 comma b minus half, and you substitute into d init. This is the value of d init, you get b square plus a square into 1/4 minus, that is fine. So, this is the expression of d init, and we know the first order differences in region R1 when you choose east and southeast. So, we can start and go ahead and write the algorithm for region R1. Yes, you can do that, but I think we will have to find out the other expressions before writing the whole algorithm to be for the curve to be drawn on the region R1 as well as in region R2, which will complete the first quadrant. The points to be selected in first quadrant. So, the we have to find out, we know the condition when you move to the next region. Okay, we will see that right again, and we will have a new d initial value in that region R2. We have two different choices. So, the first order differences also will be same, but if you look back into the slide, there is one small point here, that if you are looking for an integer based algorithm and the initial value of d itself is a fractional value, because you have a 1/4 minus b here. Now, only of course, if a square is an even quantity, it might cancel out, otherwise typically you might start with a fractional value here. Now, this is going to be causing a problem. It will slow down when you have floating point arithmetic instead of integer arithmetic. We had this problem in a case of a circle. We had the d start, okay, as h minus 1/4, a value of 1/4 also came out in the case of a circle. The same thing is coming out in the case of ellipse. What to do? What was the solution we adopted in the case of a circle? Well, the solution was, yes, we multiplied the entire function f by such quantity or change, substituted the value of. So, you can use the mechanism which we used in case of a line, where you multiply the value of function by 2 or 4 as the case may be, or you resubstitute and get a value h is equal to d minus something and get rid of this fraction. I think in this particular case it would be advisable and easy to look where we multiply the d init or the function value f by a value 4. If we multiply it by 4, then your d unit value will be 4b square plus a square into 1 minus 4b. So, that becomes, you can start with an initial condition. I will not write that equation, but I leave it to you as an exercise to work out with the new d unit value, which is an integer, and then also start ahead and find out the first order differences for east and southeast with the new value of 4 times f. So, that I leave it to you. I am not discussing this. I go ahead with this set of expressions as it is, and also write down the algorithm. The rest part of it, how to make integer starting from the d unit value, is left to you. Okay, please do that. Please make a note of that, that the d unit value is a floating point. So, you have a problem with a fractional or a floating point value of d unit, but by now, if you have followed my previous lectures for line drawing and circle, where we knew how to draw where we knew how to start with the integer value in spite of the value starting value being fractional, we know to handle this particular case as well. Okay. Initial value in region R1 is known. First order differences in region R1 for the choice east and southeast pixel are also known. Okay. And we also know when to switch to region R2. Keep checking this midpoint. As long as this condition is not satisfied, we are in region R1, and we keep on incrementing, take a decision based on the sign of the value of d, and then update using the first order differences for east or southeast as the case may be required, and then switch only to region R2 when this condition is satisfied. We start from 0 comma b and keep incrementing, keep choosing east and southeast, one of them, east or southeast in fact, and then move to region R2 when this condition is satisfied. So, let the last point in region R1, it could be an arbitrary point, be xk comma yk. It is at this point xk comma yk where we find that this condition of switching to region R2 has occurred, and we have now moved to region R2, where the choice, if you remember when we were in region R1 in the first quadrant, the choice was between east and southeast pixel. The curve was moving almost from a horizontal manner, and then it tends to become vertical in the lower part of region R2, in the lower part of the first quadrant, and the slope is in fact numerically in absolute terms more than 1, and the choice now, since the curve is steeping down, will be between south and southeast pixels. Okay. So, we need to have a new value of d init in f of m2 depending upon xk yk. Xk yk, I must admit here that it is the last point in region R1. So, the next point is coming in region R2, but based on this we can actually find out the initial value of d in region R2. So, and since the choice is between south and southeast pixel, the yk minus 1 factor comes in for the next midpoint, the first midpoint in region R2, and xk plus half. Earlier it was the other way around, we had xk plus 1, yk minus half for region R1. In region R2 it will be yk minus 1, you will be always decrementing by 1, and xk plus half, that is between, if you know all these expressions now. The choice is between, I repeat again, between south and southeast pixels. So, that is the new d init for R2, and the top we have the d initial value for region R1, d initial value for region R2 is known, first order differences in region R1 are known as well. The only fact which remains are the first order differences in region R2 in the first quadrant. Okay. Now, d old is the f of m2 which we have derived, which we have seen the expression in the previous slide, xk plus half yk minus 1. So, it is substitute and break open the expression, you get it as this for f, xk plus half whole square, a square, and yk minus 1 comes here. So, this is the d old. If the choice is southeast, again the same condition, that means the curve is closer to the southeast pixel and d is negative, that means the point is within the curve, the d new value will be xk incremented by 3 by 2 yk minus 2. I think that you can easily find it out, because if you have chosen southeast, you would have chosen yk minus 1 and xk plus half anyway, and so the next xk plus 1 yk minus half. So, the next midpoint will be yk minus 2 and xk plus, that's. So, break open that expression, and this is what you get as your new d new. Try to express this in terms of d old plus a factor to get the first order difference. So, to basically get the first order difference, what you have to do is subtract d old from d new. If you subtract here, you can see here only the constant term a square b square cancel out, and you have terms of b square with x k and a square with y k also. Have you worked it out? How much did you get? Okay, so it will be d old, just check it out, this is the answer which you should get. It should be d old plus b square multiplied by 2x k plus 2 and a square of minus 2y k plus 3. So, this is what is going to be your d new. So, if this is your d new, which is d old plus this factor, absolutely simple to write the first order difference. Under the case you have chosen southeast in region R2, those are the subscript meanings. Southeast 2 means region 2 and southeast pixel of the choice. This is your first order difference on delta d, okay, under region 2. Let us look at the other case. If you are choosing south, the value of d again will be positive or equal to 0, and in that case when you are choosing south, the next midpoint will be incremented by half along x and minus 2 along y k, and if I break open the expression for f, this is what I get for my d new. So, now what again I have to do? The same thing, I have to express this d new in terms of the d old expression given above plus a factor which will be basically my first order difference under the choice of south in region R2. Okay. So, subtract and get, yeah, you can see that the b square terms completely cancels out here, and you are left with the term of d old plus a square minus 2y k plus 3. So, this is the factor difference between d old and d new under the case when you have chosen south, and hence the first order difference under the case when you have chosen the south pixel in region R2 is given by a square 2y k plus 3. So, now it is easy and straightforward for you to visualize that these are the two first order differences in region R2, and I hope you have noted down and worked out the first order differences when we were in region R2 in the first quadrant. We also had a delta d east one and a delta d, that is the first order difference southeast one, delta d E1 and SE1 for region R1, and for region R2 we have delta d south 2 and southeast 2 under region 2. Okay. So, these are the four first order differences which we have for the two different regions. In each region we have a pair of choices. I again repeat, region R1 the choice was between east and southeast, in region R2 the choice is between southeast and east pixels. There were two such pixels within which the curve was basically passing. The two pixels the curve was passing here, east and southeast in region R1, in region R2 south and southeast the curve was passing through the middle. Okay. So, that was the, you remember that picture which we started from today. So, where do you stop? We started, we had a d in it, initial value of d for region R1. We also found out the initial value of d from x k y k. After we move from region R1 to R2, we know the initial value of d of region R2. We have to stop the iteration. Stop basically very simple when the value of the integer coordinate y is equal to 0 here, because you keep on decrementing the value of y in any case in the region R2 all the time, and you will reach a value when y is equal to 0 from a positive value. Okay. So, let us look at the algorithm in C type of a code for the midpoint ellipse algorithm in terms of, and it requires two values a and b. Okay. A and b as the major axis parameter and the minor axis parameter, and the value could be the intensity of the beam or the width of the ellipse being drawn, or the intensity of the color. It could be the color of the elliptical curve, it could be the width of the curve, or it could be other attributes, drawing attributes like let us say the intensity of a gray shade of a color. So, some value you are passing, but main two parameters for selecting the pixels are nothing but your major axis parameter b and the a and the minor axis parameter b. Okay. So, once we know this, these are the initialization steps necessary before we move on to the iterative method of finding out the points in the two regions. Define a double variable d2, integer value x and y, and you also have a decision variable d2 and d1. d1 is for the region 1, d2 is for the region 2. Now, I must admit here that the expressions we got for the first order derivatives and also the initial values are on floating point numbers. So, I am just showing you, I am in this case showing you the algorithm with floating point, but integer based increments all right. Okay. And there are two things which are missing here, which I am leaving to you as an exercise. The first thing is change the initial value from the floating point to an integer one. So, you know that we discussed about that just a few minutes back. You have to change the value of f by multiplying by 4 if there is a factor of 1/4. That is number one. The other part which I am leaving you as an exercise as well, what we did for a circle. In the case of a circle, we saw that the first order differences are not simple constant quantities. They are functions of the integer coordinates. So, at each iteration stage, now you need to multiply with x and add. So, that was becoming costly. So, we moved to a second order difference, correct. So, please do that for the ellipse as well. When you did for a circle, I am leaving it this as an exercise for you, where you find out the second order differences. In the case of an ellipse, as we did for the case of a circle, separately for region R1 you have to solve, separately second order differences for region R2. Do not mix them up, solve it, do whatever was done in the case of a circle, do that for ellipse and come up with a new modified version of the ellipse algorithm. What I am going to show now is the using the double or the floating point initial value, but integer based algorithm based on first order differences. Okay. So, we have a floating point value of d1 and d2, which are the initial values for the decision variable d, and d1 is for region R1, d2 is for region R2, which will be evaluated in due course of time as we move on. d1 we start with, and we have the other constants SA and SB as square. So, 4-way symmetrical pixel plotting is done by the ellipse points xy value. Value could be an attribute for an ellipse, it could be the width of the ellipse, the color or the gray shade, okay, or the intensity of the beam which you want. So, that is done. So, the xy takes care of the other 3 points, symmetrical pixel plotting. And the first condition, remember we were in region R1 as long as this condition holds good. As long as this condition holds good, we were in region R1. So, this SA and SB are defined on the top, a square and b square, nothing else, and y minus half and x plus 1. Okay. So, as long as this is holding good, if d1 is less than 0, select east, increment the decision variable by 2x plus 3 multiplied by SB. 2x, this is bitwise manipulation of x, which will make x double. X is an integer anyway, so I can do a bit manipulation. This I hope you follow the syntax of C, most of you. Otherwise, this operator indicates that is a bitwise operation to multiply x by value 2. Okay, so that is very simple. C-like notations, or select southeast if d is positive or equal to 0, and increment d1 by 2x plus 3 multiplied by b square plus a square multiplied by minus 2y plus 2. Okay. So, do that and then finally increment decrement y, that you have to do if you are selecting southeast, and always at the end outside the if then else loop you always increment x, because the choice is between east and southeast, and you also draw the next ellipse points based on the new x and y. So, the region 1, this loop will keep continuing as long as this condition of the while which is put inside that continues. Then we are in region R1, when it is valid it will come out of this loop and go into region R2. So, we have to go to region R2 with the next point x comma y, which is the expression x k y k which we used earlier, and we have the new decision variable for region R2. Okay. We have a new decision variable for the region R2 and that is a function of the last point of the region R1. So, from there we know the functional form of the d init 2, we have seen that d init R2, we have evaluated that point. So, use that functional form in the expression form in this algorithm to get the starting value of d in region 2. Okay. So, that is what is given. d2 is the initial value of decision variable in region 2, x and y are the last point in region R1. So, it is basically if I say this is b square multiplied by x plus half square plus a square plus square of y minus 1, of course, minus a square b square as usual, that is anyway there. So, we put a while loop for region R2, now we have entered, and keep doing this with the condition as long as y is positive. You have to stop, the terminating condition was y is equal to 0. So, we keep on looping as long as y is positive. In this loop, we check if the decision variable d2 is less than 0, that is if it is negative, then we are selecting southeast and then incrementing the decision variable in region 2, that is d2, by the expression. You have noted down this expression, you can check out with the expression given here. In a C type of code, it is nothing but b square plus b square multiplied by 2x plus 2 and a square multiplied by minus 2y plus 3, and then of course increment x if you are selecting southeast. In the else condition, when you are selecting south, you do not increment x, all right, but you increment the decision variable d by a square multiplied by minus 2y plus 3. Okay. So, it is a square multiplied by, these were the, just check the expressions which you got earlier with what was written in this programming in the syntax as given in this code here. We have done this syntax for the case of a line and the circle, and we are doing it for the ellipse. Of course, we had two versions of the circle. I am giving you the version 1 for the ellipse, and I leave it as an exercise for you to get the second order differences and come up with a version 2 ellipse algorithm. So, that will be an exercise for you as well. So, we have the two conditions for selecting southeast and east, and also incremented the decision variable d, and of course, out of this if then else, since we are in region R2, the choice is between southeast and east, we always have to decrement y. Okay. We always have to decrement y, and like we in the region R1 we were only always incrementing x. In this case, we have to always decrement y when we are working in the second quadrant, and ellipse points will draw the other points based on symmetry. So, that completes the code. I will repeat, I will give you the first page of the code which is given here for region R1 along with the initial conditions. If you have anything to note down, please note down here, and then compare with the expressions which we did together and solve out for the first order differences in the case of east and southeast in region R1, and then of course, in region R2 we also found out the first order differences for southeast and south. Okay. So, that is what we have all done in terms of the ellipse algorithms. Okay. So, that completes the method of scanline and ellipse. We will stop with one small picture in case today where this is an illustration of how things can go wrong in trying to draw an ellipse. Now, this factor is related to the problem of the jaggies in the case of a straight line as well as in the case of a circle. There are ill effects when you are trying to draw fat lines or fat circles, and or multiple lines with one after another successive lines with different colors. We had an endpoint ordering problem, if you remember. So, these were the problems which we had in a discretized environment, and it can also happen in the case of an ellipse, and this is an example which can show you how bad or worse it is. In this case, it could be a circle or an ellipse, does not matter. What we are trying to do is basically draw a fat circle, and this can be done by, let us say, taking points on an ellipse and expanding not along x and y, but basically we draw 3 ellipses or 3 circles with 3 different values of a and b, or 3 different values of the radius r. Okay. And if you do this, the uncertainty which often comes is that you often may leave certain gaps here. So, these are certain things which will be considered in the case when we discuss towards the end of the series of lectures on visual effects and how to avoid the jaggies, aliasing problems, staircasing effects, discontinuities which can come. We will discuss much towards this end, but you just keep in mind, in spite of this, working with a fantastic algorithm which is going to speed you up, give you very fast results in terms of choosing pixels, you will have problems of staircasing, jaggies or aliasing, as well as endpoint ordering and drawing fat lines. So, these problems of discontinuities will always be there in discretized environment. Okay. This is only an example to show. So, this is which, and in some cases when you draw and we get some results like this, the quality of the picture does not become satisfactory at all. Okay. So, that brings us to the end of the lectures on scan converting lines, circles and ellipses, and in this section basically what we have done is spend the first 1 or 2 hours on drawing lines, then of course a major on circles where we found out a version 1 based on first order differences, a version 2 algorithm based on integer differences, and then of course we move to the case of an ellipse where of course we have done only, I would say, a version 1 algorithm which is based on only first order differences, and even the initial value had a floating point problem. And I would request you to take as an exercise the first exercise. I will give you a list of exercise problems as a take home exercise, and which you should solve it, and also helps you, and you should come up with an environment, a programming environment which you can come up, write a small code and see how the points come up, and then plot it in a graph paper or plot it on the graphic screen and see how it comes. But the first task should be now is take the ellipse algorithm which we have just discussed today. 2 changes you must first make. First is the the initial value of d must be made an integer integer value. So, that the entire algorithm becomes integer based, that is number 1. Then you should change the version 1 to a version 2 by second order differences. So, calculate the second order differences in region R1, okay, when the choice is between east and southeast, and use and attempt to see if these second order differences can be used to come up with a completely integer algorithm, where within each while loop you only add integer values, but not function of x and y coordinates, which we have seen just now. This is the same as the version 1 circle algorithm, is the same as this version 1 ellipse algorithm, where within each loop we are adding the first order differences which are functions of x and y coordinates. So, we have to do a multiplication addition within each loop, which could make the program very slow or the algorithm very slow and overhead and within each loop. Either we are talking of region R1 or region R2, any region, any choice east or southwest, we have the first order differences to be functions of x and y coordinates, and that is a version 1 like the version 1 midpoint circle algorithm, correct. The second version of the midpoint circle algorithm was based on second order differences, which were integer values. So, try to find out if these second order differences in region R1 and R2 are integer values, and if they are integer values, you can come up with a modified version 2 algorithm for the case of an ellipse based on the second order differences, where within each loop you use second order differences to be which are constants to update the first order differences first, and then that is used to update the d. Look, remember the version 2 of the midpoint algorithm for the case of a circle. So, attempt that same thing in the case of an ellipse. I will list you some problems to solve and take home, and that the first one which I am talking about is work out the second order differences and modify the ellipse drawing algorithm and come up with a version 2. Of course, this work should also include changing the initial value of the decision variable d to an integer. So, do that first and then look at second order differences and see if you can come up with a completely integer based algorithm for ellipse, as we have done in the case of a circle. The second task is use the midpoint algorithm and consider the symmetry to scan convert the following curves in the interval -10 to +10, okay, integer values between +10 to -10, and two curves are x equal to y square and y equals x cubed by 12. So, these are typical the case of a parabola or a cubic equation, unlike the case of a line or a circle or an ellipse. This curve in fact in the case of a parabola, so try to work it out and see what are the case, and you can probably come up with an algorithm to draw a parabola in addition to circle and ellipse, and also draw a cubic expression y equals to x cubed by 12. So, but use the symmetry to find out these curves between -10 to +10. The third problem is obtain the integer pixel coordinates to scan convert a line using Bressenham's line algorithm from a value 0, 0 to 24,9. If you see the starting point and end point, this line is going to lie in which, okay, it's going to lie in which quadrant? Of course, it's going to lie in the first quadrant only, 0, 0, 24, the slope is more than 1. So, it's basically in the second octant in some sense. So, you have to do those manipulations of swapping points and interchanging x and y values, go back to the algorithm and see what is to be done, and find out and implement the Bressenham's algorithm for this particular example. The last is use an ellipse drawing algorithm, either what we have solved using first order differences or that which you obtained from the problem 1. So, use ellipse drawing algorithm and that derived from problem 1, that is the algorithm which you derived from problem 1, use both to draw an ellipse with parameters a is equal to given as 8, b is equal to 6. We have taken examples for the case of a line and a circle with certain numerical values and obtain the x, y coordinate points. We did not have time to take an example in the case of an ellipse. So, I leave it as an example as exercise for you. Please solve it out individually and just then find out the x and y points, okay, and see if they are correct or not, because when you exchange your notes and check up the values, then you can tally the results and find out if they are same or not. So, a is equal to 8, which is the major axis parameter, minor axis 6, and then solve and obtain all the points on the ellipse using the algorithm which is based on first order differences, the ellipse drawing algorithm which we have worked out today, and also that derived in problem 1. So, problem I am saying obtain the second order differences and get a version 2. So, use that also to solve and get the points as well as the first order differences point. So, these are the 4 problems. If you are able to work out yourself without much of help, you have understood the lectures very thoroughly. and please revise all the equations we have gone through, revise all the algorithms, try to work out examples given in these lectures, slides and talks which I have given, and also some others given in the books and also in the exercises. And if you can do that yourself with little bit of practice, you will be quite efficient to solve problems in algorithms for scan line drawing, drawing circles and ellipses. Thank you.